I'm going to talk about the distribution of averages from samples of a known population. So I'm going to start by introducing my key. When you see the letter W, that is with replacement, which means that we are taking, for instance, if we have these cards, we take one card out, then we put it back, and then we grab the next card and we pull that out. So we can still get two twos if n equals 2, like here. And that does make a little bit of a difference. It makes a difference in the small population. With a large population though, we could pull without replacement, and we probably have plenty of the 2's there in that population, enough that it doesn't make a significant difference. So we have with replacement and without replacement. I use a small sample here, and we go through some of the math here. But as the size of the population and the size of the sample both increase, but the size of the population is much larger than the size of the sample, we start to see that the normal distribution occurs with looking at averages. And you can look at an average that you get with one sample, and you can use the normal distribution to predict what the confidence is that you are within, how far away, or at least whether you're within an interval of the actual average for that whole population. You can find out what the probability is of that actual average being the same as the average that you calculate. In this case though, we're actually looking at a case where we know what the population average is, and we know what the population standard deviation and variation are, the variance are, and then we're determining, we're basically finding out the probability of this, of what we get, or we can at least find the probability of that with the z-value, of getting a certain average that is within that interval. And I'll talk a little bit about that later. So with replacement and without replacement, the sample average is represented by an x with a line over it. So in this case, we're going to use a sample size of 2 just because it's really easy. So if you take the two numbers that you get, you add them up and you divide by 2, you get your sample average. Mu represents the average of the population, usually, unless we're using it to look at the average of all the averages, but it's the larger average. N, lowercase, is the sample number. In this case, we're using 2. Uppercase N represents the population size. So that's the number in the population. We're using 5, because we have 5 cards here. They're all in an interval of 2. Just to make this simple, make it much easier to make this square. And also it helps us realize how when we look at the average, we start to see more of a normal distribution, which I'll get to later. When you see sigma squared, that represents the variance. The variance is when you take each of these values, for instance 2, we know the average is 6 because we can take 6 plus 6, 2 plus 4 plus 6, that's 12, plus 8 is 20, plus 10 is 30. We divide by the number of cards here, which is 5, and we get 6. So we know that the average is 6. We take the 2 minus the 6, we get negative 4. Negative 4 squared, though, is 16, because we take that 4, the difference of 4, we square it, that's 16. We take 4 minus 6, we get negative 2, we square that, we get 4. So that's what, 20 now? 6 minus 6 is 0. Then, so we can actually, it's going to be actually symmetrical. So we already know 16 plus 4 is 20, we get 40, and then we divide 40 by the 5, and we get 8. Our variance is 8, sigma squared is 8. We take the square root of that, and we get the standard deviation, which is 2.82, which I have illustrated by the black lines on either side of the average, which is 6. You can see that here. And I've also illustrated using area. So when we're at 2, we're 4 away. But if you square that, you're making a square. And then with 4, you're only 2 away, and you're making a square there. And then on the other side, we have 8. We're making a little square here. When we're at 10, we're 4 away. This is 16, 16. And then the 4 and the 4. So that makes 8 plus 32. That's 40. But then we divide it by 5, and we get 8. So 8 square units is this. It's represented by this. If we just take the width of this black square here, we get the standard deviation. And I showed it on either side here. So that's what these black lines are. You'll find that when we use the averages for a value for 2, for example, if we're using width replacement, you'll see the purple lines on either side. They're closer in because we're canceling out the differences. Some are greater, some are less than the average. When we add those together, they're actually canceling each other out a little bit. So when you look at the average, it's actually going to have a lower variance because variance, remember, is squared. So it could be a negative value, like in this case, 2 minus 6 is negative 4. What about 10 minus 6? That's positive 4, right? Well, when we're averaging, those cancel out. But when we're looking at the variance of the actual raw population, we have a higher variance because the 4 and the 4, both of those squared, added together is 32. But actually it's 0 if we're looking at just the average, if you think about it that way. But we're actually using the denominator. The denominator is actually the average of the two numbers. So it's not exactly correct, like I said. But it still cancels out a little bit when we determine the variance of the averages versus the variance of the individual values in that population. And so I've sort of illustrated that here. So that's what sigma squared is. When you see just sigma by itself, that's the standard deviation, which is the square root of the variance. And then when you see z here, that is an individual value minus the average for that value, divided by the standard deviation, which we will actually touch on down here. Once we derive this part here in the denominator, which is the standard deviation of the population divided by the square root of the number of the sample, that becomes our standard error, and we can divide our average minus the average in the population. This is the average of the sample, average in the population, we subtract those, and then we divide by the standard deviation, which is the standard error, which is the standard deviation of the population, divided by the square root of n. And I'll show how we figure that out. So, basically though, z is the number of standard deviations away from the average that a particular value is. So when we're looking at the bell curve, z might be 0.5. If z is 0.5, it's between 0 and or if it's negative, if it's positive, I guess, it would be between 0 and positive 1 standard deviations. So if we were to look at it like that, and we want to know what the probability is of it being either at 0.5 or greater, we can just take this amount of area of the probability out of 1, because this blue part is 1, and it goes on forever in either direction, but it gets finer and finer and finer. So if you take the area that's that direction from it, if it's above it, you can find the probability of having an average that's that far away from the actual average. If we're putting in terms of z, which 0 is actually, if it's exactly the same as 6, which is the average we get here in a little bit. 6 is actually right in the middle of both of them, and I already told you how to derive that. So this grid here is two-dimensional. It's two-dimensional because we chose n of 2. Our sample size is 2. Our actual population is 5. And there are 5 values here. And I also put the other 5 values here. So if we're choosing width replacement, we can consider it this way. We can look at all 25 of the squares. These are all averages. We take 2 and 2, add 4, divide by 2, we get 2. We take 4 and 4, 4, 6, 8, 10. If you go down this, these are the same. But on either side are the other ones where they're different. They're not the same exact number that you draw. Obviously, those comprise the majority of this. But whenever you see red down here, this is without replacement. Whenever you see purple, I chose purple because it's blue and red, that is with replacement. But those come out to certain values. For averages, they're all the same. But for the variance, they're different. And you'll find that if we take the variance of the actual population, we get 8. If we take the variance with replacement, we get 4, and that is 1/2. It takes 2 of these to get 8, right? 2 times 4 is 8. 2 is our sample size, and you will always find that if you're doing it with replacement, you're taking the card, putting it back, and giving a chance of getting that same card again. And in a larger population, you have about an equal chance of getting the other card because there's so many cards. It's going to be representing about the same amount as before, even after you take it out. So that's the idea here. You will find that the variance is 1 divided by the sample size of the variance of the actual population, which I'm going to show you here in a little bit. But keep in mind, there are 25 of these. If we're going to, and before I get to this part, I want to show you a histogram. So this histogram here, this is xi, which means any particular value that you pull out here. If you look at how well represented they are, you see that 2 is represented once, because there's only 1, 2. 3 is not represented at all, because it's not one of these numbers. 4 is represented 1 time, and so on. You go down, 2, 4, 6, 8, 10. There's one of each of those, right? But if we're taking 2 of the cards out, we're adding those up and we're dividing by the sample size, which is 2. You get the average. So if you look at these as averages, when we do it with replacement, we have 1, 2, 3, 4, 5, and then it goes back down again once you get to 7, 4, 3, 2, 1. You see this pattern here. If this was, so the first value is 2, and then the last value is 10. That's what you see. If you're sampling without replacement, that means you have 1 less there now, so you cannot get 2 2s. That's why this blue area is off limits to the red area, because you cannot get 2 from the 2 and the 2 and the 4 and the 4. You can't draw the same card twice because you took it out and you only have these ones left, right, in the population. So I showed 2 different ways to do this. We take the averages, they still come out to be 6. So before I get there though, if you look at without replacement, you have 2 of the 3, but you don't get any of the 2. You don't get any of the 10. 2, 2, 3, 3, 3, 2, 2. If you look at how this is, both of these are starting to form a mound. Now consider this. These are not normally distributed. 6 should be more represented than 4 or 8, and 4 and 8 should be more represented than 2 and 10 in a normal distribution. Even without that though, you can see how you get more of a mound with this. If you were just to take this, you would just have it would be like a square wave basically, every other. 1, 0, 1, 0, 1, 0, 1, 0, 1. You just keep going. So to figure this out, so if we want to get the denominator of how many different ways there are to choose an average, because you got to choose 2 cards. So if we're replacing it each time, we can just take n, the number 5 in the original population, raise it to the sample size, because we're putting it right back in, we can raise it to that sample size. So the population size raised to the sample size, we get 25, because 5 squared is, 5 to the 2 is 25. Now, if you want to look at the permutations for taking card out, and we have some left over, we're taking 2 cards out, and we have 3 left, right? So we take 5 factorial divided by, in parentheses, 5 minus 2 factorial. When we do that, we get 20. So that is our denominator down here. When we're taking the average, we're dividing it by 20, and we're taking all 20 of the red ones there, we're adding them all together, and we're dividing by that 20, we get 6. Okay? Here, we're using 25, 5 to raise to the 2. Here we're just using the 5. We're taking those 5 values and then adding them together and dividing by 5, we get 6. Now when we want to find the variance for the original population, that's sigma squared, and that equals each value, like I said before, you're subtracting the average from them and you're squaring them and you get 8, which we already talked about. When you use each of the 25 values, you do the same thing. You take each individual average that you get, you subtract from the average of averages, which is still going to be 6 because we just determined that over here, the average of the averages. We subtract those and we square them, and then we divide by the total number of possibilities. We get 4, and that is half of 8, like I said here. Sigma squared divided by n, that's going to be the variance of the average with replacement. Without replacement, though, it's a little bit different. When we do the math, we get 6, though, but here we take each average, and then we subtract the average of the averages, which is 6. We square it, but we're dividing by a different denominator. In this case, and we're not using these 4 values here. So we have a smaller number, and we have a different denominator, and we end up getting, the denominator is 20, we end up getting 3. The relationship between 3 and 8 here is actually the same as, I'm showing it in an equation here. You'll find that this is the case with other cases if you use different n's for both. You get the average, the variance of the average equals the variance in the population times the size of the population minus the size of the sample, in parentheses, divided by the number of your sample times, under this, the size of your population minus 1. Now notice though, if n, the size of the population, the capital N, is much larger than the sample size, you can pretty much make this n. So n minus a small number is going to still be about n. N minus 1 is going to be pretty much the same as n. So you basically can say that it's actually the variance of the population times n divided by your sample size times n. These n's will cancel out, and you'll end up with the variance of the population divided by the sample size. That gives you the variance of the average. When you're not using a replacement or when you're using a replacement, they're both going to be the same thing if the population size is much larger than the sample size in the case of without replacement. But even with replacement, it still gives you the same thing. So we can basically if we take the actual variance, we want to find the standard deviation, to use this formula here to find a z-value for our average, to see where it is in this. So when we take the square root of this, we take the square root of the variance of the averages, we end up with the standard deviation of the average being, this is the standard deviation of the average, and it equals the standard deviation of the original population divided by the square root of n. So in generally, if the sample size divided by the population size is less than or equal to 0.05, then the standard deviation of the average equals the standard deviation of the population divided by the square root of n. And I've just shown this here for you. Notice that 4 is 1/2, and then we use 2. If you try other sample sizes, you'll find the same thing. It takes a lot of work though, because once you go up to n equals 3, you have 125 possibilities, but still n needs to be a much larger number for this to really be applicable. When you do that though, now we can take z, since we already know what the standard error is. The standard error for the average is the standard deviation of the original population divided by the square root of n. We can take this amount here, we can plug it in for the actual standard deviation up here, and instead of just an individual value of x, we can take the average that we get for a particular sample that we pull out, We take two cards, take the average of them. We can take that, we can subtract it from the average, which is 6. 6 here in the original population. And we divide it by that standard error of the standard deviation of the original population divided by the square root of n. The reason this is the square root of n, by the way, is if we take the square root of this is already sigma squared, so it becomes just sigma here, right? The n, though, becomes the square root of n. So that doesn't look as much the same. So when we have a z value, though, for an average that we already know the population for, then we actually, let's just start the other way. Let's say we already know what the standard deviation is for population, and we already know what the average is for that population. And we have somebody else choose 2 of those, for example, out of this. We can use the z value here. We can find 95% confidence, for example, by knowing that it's going to be about 1.96, which is probably pretty close to -2, if it's negative 1.96, positive 1.96 standard deviations for the z value here. If we do that, we can know that it's going to be within this interval 95% of the time. And so it doesn't seem that practical right now in this case, but this is a foundation for actually determining whether, when you pull a sample and you don't really know the values for the population, or you can know some of them, you can still kind of get an idea of your confidence level on either side of the average you got for the actual average in the population. Because the more that you have in the sample, the closer it's going to be. And you can even see that here. The more that we had for n, the narrower it got for that standard deviation. And like I said, the central limit theorem in statistics says that as you increase the size of n, as long as if n is lowercase n is much smaller than higher uppercase n, if you do that, it's going to basically, this value here is going to get closer and closer to 0. It's going to get smaller. So you're going to get a narrower confidence interval. It's going to be much closer to the value of the average if this is normally distributed. And you can see that the more that those other people pull of a sample from the whole population that you already know about, the smaller their interval is going to be from the actual average. They're going to be somewhere closer and closer and closer and closer. The reason for that is, the probability of getting an extreme value twice is much, much lower with a higher number that you're pulling from a larger population, because it's still really improbable. Look, 2 is only represented once, 10 is only represented once here. The closer you get to the middle, the more likely it is, because you got 5 6s here, you have 4 5s and 4 7s here. This right here is actually more than half of the area of this whole thing, because you have 5 6s, you have 4 5s, and 4 7s. So 4 times 2 is 8, plus the 5, that's 13. That's already more than 12.5, which would be half of the 25. So already half of the numbers are right here. And those are just those 3 values. So they're probably going to have an average of 5, 6, or 7. You can already figure that. And the larger the population, the more that you have in your sample size, the closer it's going to be. They're going to probably get a value very close to the middle here. If you're looking at it diagonally on an odd and even axis of diagonals, you're going to see that it gets pretty close to that. So I touched a little bit on the central limit theorem, and basically the reason for that is, the reason for the central limit theorem, basically the foundation of it is, when you get more numbers from that population, they could be on the lower side or the upper side, red or green, but when you add those together, they're canceling each other out and they're getting closer to the middle. And with the variance for here, we're taking each individual value. If it's different than that, we take the difference, we square it, right? Which you can see, if it's a difference of 2, we take 2 squared here, And if it's a difference of 4, that's 4 by 4. And we add these areas together, then we divide by the number. This is 1/5, this black area here is 1/5 of the area of this square, that square, and that square added. 6 is 0, so there is no square for 6. But if you take all those squares, you add them together to make that larger area, then you divide by the number in the population, you will get this area here. And if it's a perfect square, this dimension here is the standard deviation. And you find that it gets smaller when you have an average, because you're using more values and they can cancel out. You're not just adding the variance. That variance is smaller and smaller, but you're using a different denominator. You are using whichever average you have, but if you think about it though, it's a smaller and smaller area. So this red area is without replacement, this purple area is with replacement, and you can see these areas are smaller than this area here. And so that's the idea behind the central limit theorem, and this shows the relationship between an average, like the variance of an average versus the variance of an individual. That's why the more you have in your population and the more you have in your sample, if your sample is still smaller, much smaller than the actual population, you're going to get a closer and closer number for your average to the actual average in the population. I hope you enjoyed this, and thank you.